Welcome to calculus class. Today we are going to learn about representation of functions by series. Now, this first problem we're going to do two different ways. And the first way is the way that I prefer to do it and the way that I'm going to stick with. The second way, though, I would just like you to see for exposure so you know that it is another method that can work on these problems. So we've got a function f of x equals 2 over 5 minus x. So this is a rational function and you can see that the center, it's centered at 0, and we're going to keep it that way. And so our first step to rewriting this as a series, we're going to make a series that represents this function, is we're going to write the function in the form a over 1 minus r. That should look familiar to you. That is how you find the sum of a geometric series. So you can see 2 would be our a value, but we've got a problem here because the 5 should be a 1. So f of x is equal to 2 over 5 minus x, but this 5 should be 1 to make it look like this form. So we can force it to be 1 by multiplying the whole function by a clever form of the number 1, which is one of our fancy math tools for algebraic manipulation. And we're going to multiply it by 1/5 over 1/5 because 1/5 divided by 1/5 is 1. And when we distribute that across the denominator, this will become a 1. So we'll have 2/5 in the numerator over 1 minus x over 5. Okay? Now this is our a over 1 minus r. So this means our a value is 2/5 and our r value is x over 5. So after we've done that, step 2 is to rewrite as a geometric series. So you'll remember the sum from n equals 0 to infinity of a times r to the nth power was our basic form of a geometric series that we've learned. So we're going to make this the sum from n equals 0 to infinity of a is 2/5 times r, which is x over 5, and that's going to be raised to the nth power. Now, we've done that. Now, we've written it as a geometric series, but typically you're probably more likely to see this written like if you were to check your answer in the back of the book or see it in a multiple choice problem as being expressed in a more traditional manner. So 2 times x to the n over 5 to the first times 5 to the n. All I did here was raise the numerator and the denominator here both to the nth power. And now since these are both 5s, these can be put together as the sum from n equals 0 to infinity of 2x to the n over 5 to the n plus 1. And that would be more likely the way you would see that represented. Okay, so we rewrote this function, this regular f of x function that we could have made a graph of back in Algebra 2, as the sum of an infinite series. geometric series specifically. Now, that's one method for doing that. The other method for number 1, we're going to do this using method 2, which is long division. Okay, so I want you to consider that when you express a rational function, numerator over denominator, this is a division problem, numerator divided by denominator. So we're going to write this with the long division, 2 divided by 5 minus x. Okay, now what would you multiply a 5 by to give you 2? Well, that would be 2/5. Okay, so then I'm going to multiply it times both of these terms. 2/5 times 5 equals 2, and 2/5 times negative x is negative 2x over 5. And then I'm going to subtract. So 2 minus 2 is nothing. 0 minus negative 2x over 5 is positive 2x over 5. And then I start again. What would I multiply a 5 by to give me 2x over 5? Well, I just need to cancel out the 5, and it would be positive 2x over 25. So now I'm going to multiply 2x over 25 times both of these terms, which will give me 2x over 5 minus 2x squared over 25. And now I'm going to subtract. So the first term goes away. 0 minus negative 2x squared over 25 gives me positive 2x squared over 25. And then I ask myself, what would I multiply a 5 by to give me 2x squared over 25? Well, that would be positive 2x squared over 125, because 25 times 5 is 125. So now I'm going to multiply that times both terms, 2x squared over 25 minus 2x cubed over 125, and subtract, which would leave me with positive 2x cubed over 125. Well, this is going to continue. And if you look for the pattern, you could write this as the sum from n equals 0 to infinity of the numerator has got a 2 each time. X is going from 0, 1, 2, so that's going to match n over, this is 5 to the first, 5 squared, 5 cubed, so that's 5 to the n plus 1. And that is equivalent to what we got using the other method. Okay? Now, let's talk about the interval of convergence of this geometric series here. If you will remember, the geometric series converges when r is less, when the absolute value of r, which our value here is x over 5. So when the absolute value of r, which is x over 5, is less than 1. Here, I'll write that to the side here. Absolute value of r is less than 1. That's from the convergence test rules for geometric series that we learned previously this year. So I write that as a complex inequality, -1 less than x over 5 less than 1. Multiply each of these parts times 5, -5 less than x less than 5. And so the interval of convergence is -5 to 5. And I do not need to test endpoints because it is not less than or equal to 1. It must be strictly less than 1. So -5 to 5 would be the interval of convergence for this infinite series that we wrote. Okay, so on number 2, we have, get this lined up here, a function f of x is equal to 3 over 2x minus 1. And this time, we want the center of our series to be equal to 2. So this will add a little twist to our work. So I want you to consider that we have a over 1 minus r is how we're going to try to make this function look. Okay, so first, f of x, I might say, is 3 over, we could say, negative 1 plus 2x. So I've got my constant of 1 here in front, but it's negative, so that's not exactly right. But also, if I want the c value to equal 2, I'm going to need an x minus 2 in here. So I'm going to think about how I could algebraically make that happen. Negative 1 plus 2 times x minus 2. Now, I didn't just put a negative 2 in here because this 2 distributes, so I actually subtracted 4 in this problem that wasn't here before. So I'm going to have to add a 4 that wasn't there because I've added this negative 2 times 2, which is negative 4. So that if I have a minus 4 and a plus 4, that counterbalances so that this is algebraically equivalent to what I had previously. Now, these are like terms, so they could be combined, and I could say this is 3 over 3 plus 2 times x minus 2. And now I have a 3 out here in front where the 1 is supposed to be. So I'm going to multiply times 1/3 over 1/3. And that 1/3 is going to distribute on the bottom to both of the terms that I have here. So now my f of x function will equal 1 on top of 1 plus 2/3 times x minus 2. So this is my a over 1 minus r. So that means my a value is 1 and my r value is, now remember, minus r. This says plus, so it's going to be negative 2/3 x minus 2. Very complicated looking r there. So the way I would write this as an infinite series is the sum from n equals 0 to infinity of a times r to the nth power. So for this problem, that's going to be the sum from n equals 0 to infinity of 1 times negative 2/3 times x minus 2 to the nth power. So there's my infinite geometric series. Now I need to include the interval of convergence. Where does this series converge? So that's going to be the absolute value of r must be less than 1, or negative 1 less than negative 2/3 times x minus 2 less than 1. Now, I want you to remember this algebra rule. When you multiply by a negative, it switches the direction of the inequality symbol. So I'm going to multiply all 3 parts times negative 3/2. So this will be positive 3/2. And then I switch this to a greater than, x minus 2 greater than negative 3/2. Now, I don't like these being greater thans because I'm very used to everything being less thans. So I'm going to kind of read this backwards. Negative 3/2 is less than x minus 2, which is less than 3/2. And now it's fixed so that it looks more correct. Now I add 2 to all 3 parts. And adding 2 to halves would be like 4/2. So this is negative 3/2 plus 4/2 less than x less than 3/2 plus 4/2. So this is 1/2 less than x less than 7/2. So my interval of convergence is from 1/2 to 7/2. All right. That concludes example 2. Let's go on to example 3. F of x is equal to 2 over 6 minus x, and we're going to have a c value of -2. So another one of these where it's kind of funky. We got to have something extra with the x to make that center what we want it to be. So f of x is going to equal 2 over 6 minus x times, oh, sorry, no. I want the parentheses here. Minus x, and if it's -2 for the c, I want a +2 with the x because it's x minus c. Now, what I've just done is actually subtracted an extra 2 that wasn't here because that negative distributes. So I'm going to have to add a 2 to counterbalance that. And that 2 can get combined with the 6. So I'm going to have 2 over 8 minus the quantity x plus 2. And then I'm going to multiply times 1/8 over 1/8. And that's going to give me 2 times an eighth on top, which is 1/4. And then 1 minus 1/8 times x plus 2 down here. This is my a over 1 minus r. Oops, they're kind of close to the edge there. All right, so now I'm going to rewrite this as the sum from n equals 0 to infinity of a, which is 1/4, times r, which is 1/8 times x plus 2 raised to the nth power. And now to do the interval of convergence for this series, I'm going to say the absolute value of r must be less than 1. So -1 is less than 1/8 times x plus 2 less than 1. Multiply all 3 parts times 8. -8 less than x plus 2 less than 8. And then subtract 2 from all parts. So -10 is less than x, which is less than 6. So the interval of convergence is from -10 to 6. So we're being asked to write the series and write the interval of convergence for the series. So that is done. All right, are you ready to do one that's a little bit more involved? I bet you are. Number 4. G of x is equal to 3x minus 8 over 3x squared plus 5x minus 2, and we'll do an easy center of 0 this time. Now, how are we going to get this to look like a over 1 minus r? There is far too much going on here. In this, we only have a constant on top, and we have a lot more than that going on here. So we're going to use a good old technique that we learned not too awfully long ago, which is partial fractions. Yay, we needed to review that anyways. Okay, so how does that work? Well, if you remember, we're going to factor your denominator. So it's going to be 3x minus 8 over, let's see, 3x and x, factors of 2. We need a middle term of 5, so this would be 2 and this would be 1. We want the middle term to be positive, so a positive 6 and a negative 1. That should do it for us. So we're going to write this as a over the first factor plus b over the second factor. And now we are going to multiply both sides by the denominator of the left side. So that'll be 3x minus 8 equals a times x plus 2 plus b times 3x minus 1. And then we're going to multiply ax plus 2a plus 3bx minus b. And then we're going to regroup so that the x's are in descending power, and go ahead and factor out that x. So we're going to have a plus 3b times x plus 2a minus b for the constant. And now we're going to write a system of equations and solve it. So 3 is the coefficient of x on the left side. A plus 3b is the coefficient of x on the right side. Those go together. Negative 8 is the constant term on the left side. 2a minus b is the constant term on the right side. And now we're going to solve for a and b. If I take this equation on the right, multiply everything times 3, I get do I want to do that? Yeah. 3 times negative 8 is negative 24. 6a minus 3b. Now I can come over here and add that to this one. Negative 24 equals 6a and negative 3b. So I'm using elimination here. And of course you can use any method you want. 3b minus 3b is 0. Negative 24 and 3 makes negative 21. And then I have 7a. So if I divide by 7 on both sides, a equals a negative 3. Now I need to figure out what the b is that goes with it. So let's see, negative 8 equals 2 times negative 3 minus b. So negative 8 equals negative 6 minus b. And then add 6 to both sides. Negative 2 equals negative b. Divide by negative 1 on both sides. 2 equals b. Okay, so that is done. Now, I'm going to go back to my g of x function, which was 3x minus 8 over 3x squared plus 5x minus 2. And I'm going to write that as a, which is negative 3 over 3x minus 1, plus b, which is 2 over x plus 2. Now, this is like my a over 1 minus r, but kind of in two chunks. So we're going to have two separate kind of series rules, for one for each fraction. So it's like a 2-for-1 problem. Negative 3 over, we'll say negative 1 in front, plus 3x. So I need this to be a positive 1. So I'm going to multiply this times negative 1 over negative 1. And then plus 2 over, let's see, this is 2 plus x. I'm putting the constant in front, so it looks like this. But I need that to be a 1, so I'm going to multiply this one times a half over a half. So this is going to be positive 3 over 1 minus 3x plus 1 over 1 plus 1/2 x. So this one has an a value of 3 and an r value of 3x. This one has an a value of 1 and an r value of negative 1/2 x. So we're going to do the sum from n equals 0 to infinity of a, which is 3, times r, which is 3x raised to the nth power, plus the sum from n equals 0 to infinity of 1, which is a, times r, which is negative 1/2 x raised to the nth power. Now, this is fine. This is correct. There's nothing wrong with this, but there is a better way to write it, and one way that you would probably be more likely to find it in the back of your textbook or in the answers to a multiple choice problem. So let's look at how else this could be represented. If you had the sum from n equals 0 to infinity, you could do 3 times 3 to the nth power times x to the nth power, because this n from your properties of exponents goes to both of those factors inside the parentheses, plus the sum from n equals 0 to infinity of 1, which you don't really need, negative 1/2 to the nth power x to the nth power. Now, notice that you have x to the n in both. You can actually factor that out and make it one common sum, the sum from n equals 0 to infinity of 3 times 3 to the n plus negative 1/2 to the n, all multiplied times x to the n. And that's probably more likely the way you're going to see it. Now, let's talk about, you could even say these both have a 3 as a base and do 3 to the n plus 1. That'd be one more step you could do. In fact, maybe I'll go ahead and write it like that. 3 to the n plus 1 plus negative 1/2 to the n, all times x to the n. Now, let's talk about the interval of convergence of this series. We have a little situation here where we have two different r values. And guess what? The absolute value of 3x has to be less than 1, and also the absolute value of negative 1/2 x must be less than 1. So we're writing two complex inequalities. And we're going to isolate the x in both. Okay, so dividing by 3, negative 1/3 less than x, less than 1/3. Here, multiplying by negative 2 to all three parts means we're going to have positive 2. When you multiply by a negative, you reverse the inequality. Multiplying by negative 2, so this is negative 2. And this would go negative 2 less than x less than 2 to reorder them with the less thans like we're used to seeing. So how can we have two different intervals of convergence? What you have to choose is the most restrictive. Okay? And it is possible that you might need to choose part of one and part of the other. So negative 1/3 or negative 2, which one's going to leave out more numbers? The negative 1/3 less than x, and 1/3 or 2, which one is going to leave out more numbers? It's the 1/3. So we want this to be our interval. Oops, I wrote 1/2. I apologize. Negative 1/3 to positive 1/3. Write it in nice interval notation here. That's the interval of convergence. That's the infinite series. Okay. So, now we are going to go on to our next example, number 5. So for number 5, we have f of x is equal to 5 over 5 plus x squared, and we're going to have a c value equal to 0 this time. So we're going to do f of x is equal to 5 over 5 plus x squared. I need this to be a 1, so I'm going to multiply by 1/5 over 1/5. And that's going to give me 1 over 1 plus 1/5 x squared. So my a value is 1, and my r value is negative 1/5 x squared. So I'm going to write my sum from n equals 0 to infinity of 1 times negative 1/5 x squared to the power of n. And now I need to look at what the interval of convergence will be. So I'm going to do the absolute value of negative 1/5 x squared is less than 1, which means negative 1 is less than negative 1/5 x squared, which is less than 1. And now I'm going to multiply everything by negative 5. So I'll have 5 is greater than x squared, which is greater than negative 5. And then to get the x by itself, I'm going to take the square root. Oh wait, no, let's reorder these. Negative 5 less than x squared less than 5. We don't want greater thans, we want less thans. So now we're going to take the square root of all the parts. Uh-oh, square root of negative 5. What? Okay, this right here is not needed because it's imaginary, and we're only working with real numbers, okay? So we're going to say the square root of x squared is less than the square root of 5. Now, this is still kind of complicated because the square root of x squared is not just x, it's plus or minus x, okay, from algebra. And so what does that mean? X is less than the square root of 5, and negative x is less than the square root of 5. If you multiply by negative 1 on both sides here, x is less than the square root of 5, and positive x, multiplying by negative 1 reverses this, is greater than negative square root of 5. So x is bigger than the negative 1 and less than the small one, which means we could write it as negative square root of 5 less than x less than square root of 5. So our interval of convergence is negative square root of 5 to positive square root of 5. Okay? All right. You want to try one on your own? How about this one, number 6? F of x is equal to 1 over 1 plus x, and we have a c value of 0. So why don't you try to write this? And this one should be fairly simple, so give it a try and see if you can get that. Okay, I'm going to assume that you finished that and restarted your video. So it looks like a value is 1, r value is negative x. So you would write this as the sum from n equals 0 to infinity of 1 times negative x to the nth power, which you could also think of as negative 1 to the n, x to the n, because this has a coefficient of negative 1 and it's also being raised to the n. And the interval of convergence is going to be the absolute value of negative x is less than 1. So negative 1 is less than negative x, which is less than 1. Multiply everything by negative 1. 1 greater than x greater than negative 1. Or negative 1 is less than x, which is less than 1. Negative 1 to 1 is the interval. Now, this one, 1 over 1 plus x, and its buddy, 1 over 1 minus x, are kind of favorites to do some interesting extensions of on the AP exam. So kind of be on the lookout for those because they're fairly frequently used. Okay, example 7. F of x is equal to 1 over the quantity 1 minus x squared. Now, what I want you to notice about this function is that it is equal to the derivative of 1 over 1 minus x. And this is a equals 1 and r equals x. So if you think of the derivative of the sum from n equals 0 to infinity of this, well, let's see, a over 1 minus r, this is at, 1 and x, so 1 is a times x to the nth power. If we were to use the power rule to take that derivative, it would be equal to the sum from n equals 0 to infinity of n times x to the n minus 1 power. So that would be the rule for this guy. And that's not something that I might expect that you notice right off the get-go without me having pointed that out to you, but now that you have seen it, and I've told you 1 over 1 minus x is a really common one, that's something that I'm hoping that you will kind of be able to use moving forward. So the interval of convergence, since we don't have like the a and the r for this, we're finding the interval of convergence for this, which is not your typical geometric series. We're going to have to use the ratio test for absolute convergence and do the limit as n approaches infinity of n plus 1 times x to the n plus 1 minus 1. I'm filling in n plus 1s where I see the n's, and dividing by the original x to the n minus 1. So let's see how this works out. We've got n plus 1, x to the n over n, x to the n, x to the negative 1. So the x to the n's will divide out. That x can move up to the top. So the limit as n approaches infinity of x times n plus 1 over n. We can pull the absolute value of x out in front. Absolute value of x times the limit as n approaches infinity of the absolute value of n plus 1 over n. And of course that limit is 1 because they both have the same degree, so it's the ratio of leading coefficients. Absolute value of x times 1 equals absolute value of x. So we're going to go absolute value of x is less than 1, negative 1 less than x less than 1. And because this wasn't a strictly geometric pattern, we do need to check the endpoints. It was a manipulation of a geometric one, derivative of it. So we're going to plug in negative 1, the sum from n equals 0 to infinity of n times negative 1 to the n minus 1. Well, this one is going to be diverging because this is just going to oscillate it, and these ends are just going to get bigger and bigger and bigger, so the limit does not equal 0. So we don't want to include that. And then what about when we substitute in the other endpoint, positive 1? Well, that's always 1, so this is just 0, 1, 2, 3, 4, 5, 6, 7. So it's just growing without bound, so it's not got a limit of 0. So it's diverging, both of them diverging by the divergence tests. So we can't include either endpoint, so it's from negative 1 to 1. Neither endpoint included. Okay, so now we are on number 8. Number 8. How about f of x is equal to the natural log of 1 minus x? This one, I want you to try to make a connection with 2. This is not a strictly geometric sequence, but it's a manipulation of a geometric sequence. This is equal to the integral of 1 over 1 minus x dx. Okay, so we are going to think of this as the integral of the sum from n equals 0 to infinity of a, which is 1, times r, which is x, to the nth power dx. So how do we integrate that series? Well, we're going to do the power rule backwards. So it's going to be x to the n plus 1 times 1 over n plus 1, which is equal to the integral from n equals 0 to infinity of x to the n plus 1 over n plus 1. So this is the series, the infinite series, which represents this function. And now we need to know its interval of convergence, since it's not strictly a geometric series. You guessed it, we're going to have to do the ratio test for absolute convergence, the limit as n approaches infinity, of this series rule with n plus 1's subbed in place of the n's. So x to the n plus 1 over n plus 1 plus 1 divided by the original or multiplied by the reciprocal of the original. Oops. Started writing that like it was coming down and it was still part of the power. I hope you can read that. That's x to the quantity n plus 1 in the power. And so we're going to put that in absolute value bars, and we are going to clean it up. X to the n plus 2 over n plus 2 times n plus 1 over x to the n plus 1. So let's break it down. The limit as n approaches infinity of the absolute value of x to the n times x to the 2 times n plus 1 over n plus 2 times x to the n times x to the 1. So the x to the n's divide out. X squared divided by x to the first is x. So we'll have just one x on the top times n plus 1 over n plus 2. And then we're going to pull that absolute value of x in front and say n plus 1 over n plus 2. So that limit is equal to 1. So this is equal to the absolute value of x times 1, which is just the absolute value of x. So now we're going to go for our interval of convergence. The absolute value of x must be less than 1, which means negative 1 is less than x, which is less than 1. But we need to check the endpoints. So we're going to take our original series rule right up here and plug in negative 1 and 1 for the x and see if they are converging or diverging there. So the sum from n equals 0 to infinity of negative 1 to the n plus 1 over n plus 1. Let's see. This is alternating harmonic series, so that is not absolutely convergent, but it is conditionally convergent by the alternating series test. So we would include this endpoint. And then the other one is positive 1 to the n plus 1 over n plus 1. So this one is harmonic, because the numerator is just 1. and so it is diverging. So we're going to include the negative one, and we're not going to include the positive one in the interval of convergence for this infinite series. Okay, we are now at our last example for today, number 9. Find a power series for arctangent of x centered at 0. Okay, I want you to think about how the arctangent of x could relate to what we've learned today about representing functions as infinite series. We certainly haven't worked with the arctangent of x. We've mainly worked with geometric series. So is there anything about the arctangent of x or the inverse tangent of x that relates to the infinite geometric series? Well, sometimes you're going to have to use your thinking cap. The derivative of the arctangent of x is equal to 1 over 1 plus x squared. Hopefully you've got that on a note card and you're studying that regularly. So now, if you think about that as an a over 1 minus r situation, the a value would equal 1 and the r value would equal negative x squared. So the derivative of the arctangent of x could be represented as the sum from n equals 0 to infinity of 1 times negative x squared to the nth power, which you could also think of as negative 1 to the n times x to the 2n, because when you raise a power to a power, you multiply the powers. And so if that's what the derivative of an arctangent is equal to, we could integrate the derivative to get the original arctangent of x. The integral of the derivative of the arctangent of x dx is equal to the integral of the sum from n equals 0 to infinity of negative 1 to the n times x to the 2n dx. So keep in mind when you take the derivative of an integral or you integrate a derivative, those are like inverse operations, they undo each other. So the arctangent of x, which is what we actually want, would equal the sum from n equals 0 to infinity. This is just a multiple, negative 1 to the n. And then the x, we're going to add 1 to the power. So it's going to be x to the 2n plus 1. And then we're going to multiply by the reciprocal of the new power or divide by the reciprocal of, divide by the new power, which is 2n plus 1. And so yeah, that's done. Now as a hint, you may want to try to use this on your homework problems number 31 and 33. That might come in handy for you. Okay, now also you may want to consider what the first few terms of this series look like. If you plug in a 0, x to the 2 times 0 plus 1 over 2 times 0 plus 1. And then if we plug in 1s, and then if we plug in 2s, and if we plug in 3s, okay, and now I'm going to crunch out a few of these. Let's see, this is a positive term, x to the first over 1, negative term x to the third over 3, positive term x to the 5th over 5, negative term x to the 7 over 7. So you get the idea. Okay, that should help you out a little bit. All right, I hope you've learned a lot about how to represent a function with a series and some interesting connections along the way. Good luck with your homework assignment. Please let me know if you need any help at all, and have an absolutely fabulous day. Bye for now.